Automatic Controls, Chapter 9, Root Locus Design. This is example 1. Design a lead controller for a Saturn V rocket so that the closed-loop poles of the system occur at S equals 0.25 plus or minus J 0.25. The S will correct the instability of the Saturn V rocket, settling the pitch set point in approximately 2 seconds within a plus or minus 2% of the settling time, which is 4 time constants. So to begin with, we have been talking about the Saturn V rocket, and I'm just going to provide that here. You'll see that the plant, which is the Saturn V rocket, is equal to 1 over s squared plus, minus 0.029, which is 1 over s plus 0.17 times s minus 0.17. We've already seen the pole zero plot for that, and we know that that is got a pole on to the left of the imaginary axis and a pole to the right of the imaginary axis. So we've got to find a lead controller that not only makes the system stable but also settles it down. So first of all, we have this formula that we're using for the lead controller. This formula is found on the table on the beginning of Chapter 9 and provides a number of constants that we need to figure out. One is K sub C, which is the controller gain. One is the value of A, which is a 0 for the controller. And the final one is the letter B, which is representative of a pole. And one additional item that needs to be addressed is that for this to be a lead controller, the value of A has to be less than the value of B. Now, this same formula, as I mentioned earlier in this chapter, is for a lag controller, and in that one, the inequality is just reversed. B is less than A. So we'll start by simply looking at B. And B, the value of B for the controller, we're going to use a rule of thumb. And it's a pretty simple one to follow. In the rule of thumb, B is equal to 10 times the real part of our S. So the real part of S, that's this S that we're provided here. And you can see in that one, the value of S is negative 0.25 plus or minus J. And this is just going to be the real part. So for our situation, it's just going to be B is equal to 10 times negative 0.25, which is equal to negative 2.5. And that's the value of B. So we already know the value of the pole for our lead controller. The rest of the work that we're going to spend, and that's pretty straightforward and simple. A and K will take some doing. But I wanted to get that out of the way right away. And we can begin looking at how to find the value of A and how to find the value of K. So I'm just going to scroll this up, and I'm going to provide you with this picture of the layout of our situation. And there it is. I'm going to make this just a little bit smaller so it'll all fit here nicely. So there's our figure. And what you'll notice is that we've already put in the value for B, or negative V, which is 2.5. We've shown the two poles of the plant, 0.17 and negative 0.17. Again, one's on the left of the imaginary axis, one's on the right of the imaginary axis. We've also placed the value of our S, which was provided in the problem. Again, that's S equals, actually let me provide that to you. So S is this negative 0.25 plus or minus j 0.25. So we see the value of plus 0.25j, and here's the value of negative 0.25. There's obviously another one down here at this point, but we don't need to use it for our work here. So now that we have, we've indicated the two original poles of the plant, and again, the original poles are these two. We've also provided the value of B. Then we can determine the value of A. Now here's where we use something that you've seen before, but we've just used it in our analysis, and that is the angle condition and distance formula. And this is from chapter 8. This is the one that we're going to use right away. We're going to use the angle condition, and which is the sum of all the angles of the poles minus the sum of all the angles of the zeros is equal to 180. So let's go ahead back to our problem and figure out what that will be. So I'm going to just move this over to get it out of the way, and we'll work right here to the left of our graph. So first of all, we've drawn legs from each of the poles up to our point that was given to us in the problem. So the first one, theta 1, is from this pole at 0.17, and the length of that, so that's theta 1, and this is d1. So the distance, the angle distance from the pole to our point S is d1. The angle that our point S, the leg of this, makes with the real axis is theta 1. Clearly over 90 degrees, but not quite 180 degrees. Then we've got our second pole, and the angle that pole makes with the real axis, we're going to call that theta 2, and the distance from our pole to the point in question, S, is going to be labeled as d2. Then our B pole, which is way out here to the left, we're going to draw a leg up to our point S. That's going to have the value d3, and the angle that makes with the real axis is theta 3. And you can quickly see that theta 3 is going to be something probably less than 45 degrees, but certainly less than 90. And then we're going to add a 0. Now this 0 is from our S plus A term of our controller. And we don't know where that's going to be. I just arbitrarily picked this point. You could put it here, or you really could put it anywhere you wanted, as long as it was to the right of B, because again, it's got to be such that its value is less than b. So whatever we do, wherever we choose it to the right of our negative b pole. I chose this location. I don't know if I'm right. I could be wrong, but it gets me set up to indicate the distance, which I'm calling d with no subscript, and the angle that leg makes is going to be phi, and clearly a number less than 90 degrees. I don't know if that's right, and I may come back and say, I really wished I would have drawn it, here or something like that. But for the time being, this will suffice. So the next thing we do is we want to find the angles theta 1, 2, 3, and we want to use phi. The reason we do is we want to use the angle condition. Okay? And the angle condition says that the polar angles, which we're using thetas, minus the zero angles, which we're using phis, are all add up to be equal to 180. So it'll be theta 1 plus theta 2 plus theta 3 minus phi equals 180 degrees. So quickly we see we're going to be able to find exact values for theta 1, 2, and 3. We obviously have 180 degrees here, so that'll help us find phi. And once we find phi, we'll know exactly where this 0 will be located, just depending on this angle phi. So let's go ahead and find theta 1. So theta 1, we're going to use an inverse tangent, and so theta 1, so I'm gonna color our triangle in green here, if I can without making a mess. So, man, I'm not gonna do very well, am I? Let's try that one more time. So there's the hypotenuse. Here's the adjacent side. And here's the opposite side. So that's the triangle we're going to use. We can see right away, we don't know this angle. But we do know theta 1. And so 180 degrees minus that internal angle, or I guess I should, here, let me say it in a different way. Let's call this internal angle theta A. Well, theta A is going to be equal to 180 degrees minus theta 1. So we can rewrite that so that theta 1 is equal to 180 degrees minus theta A. So given that, we can calculate theta A, and then that'll give us theta 1. So this becomes 180 degrees minus theta 1. So that's the inverse tangent. And what is that going to be? The inverse tangent, it's going to be remember, tangent is the opposite over adjacent. So the opposite side is 0.25. So that's right here. And the adjacent side, which is this distance, is 0.25 plus 0.17. So that's going to be right here. So theta 1, when I calculate that through, and I'm not gonna whoops, I'm not going to do all that work here, but just I've got the value. That's going to be equal to 149.24 degrees. Okay, so the question is, does that make sense? And you look at this drawing, you're like, yeah, theta 1 probably is something like that. It's more than 135 degrees, which would be exactly a 45-degree angle. It's not 180 degrees, so that looks pretty good. So we'll move on. Theta 2, very similar situation. It's going to be 180 degrees minus theta B maybe. But we'll just switch to we'll skip that step and we'll look at the other triangle. So let me go ahead and draw that in. So that's going to be right here. That's that triangle. And again, got the same situation as the theta 1 triangle. So we've got 0.25 here, so 0.25. And then the denominator, it's going to be this distance right here. So that's going to be 0.25 minus 0.17. So 0.25 minus 0.17. And that angle, that should be over 90 degrees, but not 135 degrees. It should be somewhere in between. And it turns out that that's 107.7 degrees. Okay. Theta 3 is a complete, is much easier because it's got the angle is an actually internal angle. So that's going to be just the inverse tangent of, and again, let me draw the triangle. So it's this. And so that's going to be the opposite side is 0.25, same as the others. And it's this distance right here, which is 2.5 minus this short distance here. So it's going to be 2.5 minus 0.25. And that theta 3 should be a pretty small angle. And it turns out it's 6.34 degrees. Okay. So now that we've got that, we can find the value of phi, because if we rewrite this equation up here to be theta 1 plus theta 2 plus theta 3 minus 180 degrees, that's going to be equal to phi. And when we plug that in, we find that phi is equal to 83.3 degrees. Okay? So the question that I have is, did I draw my location of A, the 0 at A in the right location? No, I really didn't. It's not that it was a terrible location. At least, it's to the left. It's definitely to the left of this dotted line. This dotted line here. It's definitely to the left of that. But really, the angle should have been more like right here. It should have been right about there. And that should have been D, and that should have been phi, right there. So not bad, but not perfect either. Okay? So now that we have that, we can go ahead and find the actual value of A. Okay? Because we now know the angle, and we can use that angle to help us find the sides of the triangle. So let me clean this up a little bit and make a few changes here to make this a little neater of a problem. So if A is right here and this is the real leg, then the triangle is going to be this. Okay? We know the value of the angle. We know that this angle right here is phi. So we can use a tangent formula to find the value of A. And I'm just going to move this up a little bit. So this value here to here, we're going to call that x. That's going to be the adjacent side. So remember, a tangent of phi is going to be opposite over adjacent. So the adjacent side is equal to the opposite side over the tangent. I'm calling that x, and that's going to be the opposite side, which is 0.25. So this is the opposite side, and divided by the tangent of phi, which is 83.3 degrees, and x is going to be equal to 0.03. And the value of A is going to be 0.03 plus this distance, which is obviously 0.17. So, excuse me, not that. I misread my graph there. This distance right here is 0.25, so 0.25. So that's 0.28. And that's now the value of A. So B is equal to negative 2.5. A, so I should put it like this, to get my signs all correct. A is negative 0.28, okay? And is A less than B? Yes. So we've solved the problem of our lead controller having A less than B, so that's true. And then the next step is to find our value of K. Okay, for K, and I'm going to just change colors, so find K. And I'm going to put find K sub C. So in order to do that, you have to find the root locus gain. So first, find the root locus gain K. So we can do that by utilizing the distance formula. And now we're going to apply that to this problem. So the distance formula is just to find the root locus gain K. So K is equal to the polar distances, D1, D1, D2, D3. So D1 and D2 were the plant's two poles at negative 0.17 and 0.17. D3 is the location of B, and that's divided by the zero distances, which of course would be the location of A. So that's just, that distance is just D. So if we calculate these things out, we basically are just using the triangles created in our diagram, because we know each triangle, we know the opposite sides, it's always 0.25, and we know the adjacent sides, and then we use it to find the hypotenuse. So we're just using the Pythagorean theorem. So D1 is going to be 0.42 squared plus 0.25 squared. D2 is 0.08 squared plus 0.25 squared. And D3 is 2.25 squared plus 0.25 squared. And then the value of D is going to be the square root of 0.03 squared plus 0.25 squared. And that's going to give you approximately 1.15. So what you should notice is that each of these has the same opposite side, and that's this dotted line on the graph. The other distances are from the pole to the dotted line. Okay? So that gives us K. It does not give us Kc. Okay? The controller gain is Kc. The root locus gain is K. So what we have to do is we have to make sure we know which is which. So the way that we do that is we just do the open loop transfer function. So, so if you remember, that's going to be KGH, okay? And for the, we're basically putting a controller in, and this G is GC and GP. Actually it's all of this, and H in this case is equal to a 1. So it's going to be, first of all, GC, that's going to be KC, S plus A, and we found out A was 0.28, with a 0 at negative 0.28, over S plus B, and B is at negative, the pole is at negative 2.5, B is 2.5. And then that's multiplied by GP, and that's 1 over S plus 0.17 times S minus 0.17, and then H is 1. So when we look at this, we can see that the overall transfer function is Kc S plus 0.28 over S plus 2.5, and then I'll just put this as S squared minus 0.029. Okay, so we see here that the root locus gain is actually equal to the controller gain. So in this case only, it's not always the case, that's true. So now we have the controller gain, and it's going to be 1.15. So the total value, or the total G sub C, is going to be 1.15 times S plus 0.28 over S plus 2.5. And that's our controller. And what we know about the controller is that it's going to settle the pitch set point in 2 seconds, which is a settling time of 4 time constants. That's what we know. We'll talk more about why that's the case with this, but for the time being, we'll complete this problem, and we've now found the lead controller for this situation.